X-ray thoracic disease diagnosis with convolutional neural networks. We are Team 19. This is Ding Yaozhu with my teammate Xiaojie Du, Wenqin Yu, Jing Zhao. Our motivation for this project is that currently clinic diagnosis of thoracic disease using X-ray images is very expensive and requires domain knowledge. Here, we are trying to help build end-to-end deep learning models to facilitate physicians for the clinical diagnosis. This is our data pipeline. So we're gathering raw data, which is NIH chest X-ray images, and also we're preparing pre-processing using PySpark, Python, Amazon AWS. We also involve tools like TensorFlow and Keras, and then we building the model and having predictions. And finally, we're using RC curve to help evaluate the model and pick the best one. And we go back to the raw data. So NIH chest X-ray dataset is the current dataset we're using. They are 112,000 chest X-ray images with two CSV files. One is called bounding box coordinate, and one is called class labels and patient data. And also we're preparing data pre-processing. So there are 14 diseases labeled, and also with one label with no founding. You can see the A figure. Each of the images will have simple label or multiple label, but majority of the images just have one label. And you can see the B figure. Male are more likely have those 14 diseases than female. You can see the A figure, no founding took majority of the data set. And this no founding does not mean that the patient are healthy. They just mean that they do not have those 14 diseases in the data set. You can see the B figure, age distribution by gender. Either male or female will have those 14 diseases in age range between 35 to 65. And since we do not have sufficient data in age 0 to 10, 85 to 100, so we cannot see that those 14 diseases do not target those of the people.
The overall project pipeline consists of two modules, the data processing and the data exploration modules that are developed with PySpark, and the CNN module that is written in Python with TensorFlow and Keras. The pre-processed data is sent to data generator, which is then fed to the pre-trained models. The outcome then comes to the customized model, and then the final classification result is sent to the model evaluation. We have chosen the VGGNet, ResNet, and Inception for the pre-trained models. The VGGNet is a sequential model that consists of 3 convolutional layers connected with max pooling, and then a final fully connected layer for the activation. It is relatively simple and easy to train. Unlike traditional sequential network architecture such as VGGNet, the ResNet and the Inception models consist of the microarchitectures for feature extraction. As for the customized model, we have developed 2 types, simple and attention. The simple model utilizes a fully connected layer for the outcome, whereas the attention model still contains several convolutional layers to achieve the attention mechanism before the final output is sent to the fully connected layer with the activation. Here we compare the performance of several pre-trained models, including VGGNet 16, MobileNet, and Inception, ResNet, and NestNet. We can clearly see that VGG16 has the best performance as it has the highest average AUC score. Using the same VGG network, we can compare the simple versus attention model. The ROC curve suggests that the attention model has the better average performance than that of the simple model. In the end, we can also compare the same architecture with the default Adam optimizer versus the accumulated Adam optimizer. The default Adam optimizer updates the gradient every batch, whereas the accumulated gradient optimizer will wait for a few batches to update. We can tell that the accumulated optimizer has the better performance, and we also observe that the accumulated optimizer can boost the performance for attention model particularly. For conclusions, VGGNet has the best performance over all of the other pre-trained CNN models. VGGNet 16 plus the attention architectures achieves the best performance in terms of the AUC. Overall, our end-to-end CNN models achieve satisfactory performance for classifying thoracic disease using chest X-ray datasets. The AUC is comparable to the literature result. Thanks for your attention.